Raindrops are falling on my head, and just like the guy whose feet are too big for his bed, nothing seems to fit.
We next want to discuss the rank of an R module. Let's say that R is an integral domain and M is an R module. Then the rank of M is the maximum number of R linearly independent elements of M. We're going to prove proposition 3 that talks about rank for a free R module. So let's say that R is an integral domain and M is a free R module of rank n, finite rank n, so not infinity. Then any n plus 1 elements of M are R linearly dependent. That is, if you take n plus 1 elements of this free R module of rank n, y1 up through yn, then there exist some elements of the ring R1 up through Rn plus 1, not all 0, such that R1 y1 plus Rn plus 1 yn plus 1 equals 0. There's a non-trivial linear dependence among these elements. So no set of these of n plus 1 elements in M are linearly independent. That this definition of rank of M that we've just given shows that the rank of M is less than n plus 1. So the rank, in fact, is n. And this notion of rank matches up with the definition we gave much earlier of the free R module of rank n. All right, so let's prove this. The idea is that R is an integral domain. Instead of looking at R linear dependencies directly, we're going to first think about working instead of working not in R, but inside the field of fractions of R. Let's call that F. So we have an injective map from R to its field of fractions. We can identify a subset inside the field of fractions that gives us a copy of R. And we can do the same thing with R to the n and F to the n. So there's this copy of R to the n inside F to the n. M is a free R module of rank n, so it's isomorphic to a direct sum R plus R plus R plus R n times. And we can think of this, identify this R to the n inside the isomorphic copy of R to the n inside F to the n. So we can think of this R to the n as being a subset of F plus F plus F n times. So now we take these elements of M, y1 up through yn plus 1, and we can think of them as elements inside of F to the n. And these elements are F linearly dependent. Why? Because F to the n is an n-dimensional vector space over F. And we know that the maximum size of a linearly independent set in an n-dimensional vector space over F is n. So we get a non-trivial dependence, linear dependence, where the coefficients are now in F. F is the field of fractions of R, so we can think of those elements as a1 over b1 times y1 plus a2 over b2 times y2, where a1 and b1 are elements of R. And various other things like the b's are not 0. These are elements of the field of fractions. So we get this linear dependence. We know that not all of these elements of F are 0. And we can clear denominators, meaning we can multiply both sides of this equation by the ring element that is the product of all the denominators. And now what we're going to get is a non-trivial linear dependence where the coefficients are not in F, but are in R. So this is going to show that these n plus 1 vectors, these n plus 1 elements of M, are linearly dependent over R. So that's the end of the proof. So the big idea here is instead of working in R, work inside the field of fractions F of R. There's something that's potentially a little bit confusing here, where you have to think about M as being isomorphic to this copy of R to the n, and then we're identifying this copy of R to the n as being a subset inside of f to the n. So we're identifying the isomorphic copy of r to the n inside f to the n. Okay, so this argument uses what we know about vector spaces. Dummit and Foote give a second proof of this fact that involves determinants. So you don't need to know that for this course, but you may want to look it up. So I encourage you to look at Corollary 27 in section 11.4 and see how this gives a second proof of this result. So I'm going to pause and erase, and I'll say just a little bit about what this tells you, not just about the rank of the free module M, but the rank of submodules of M. Keeping proposition 3 in mind, let's say that R is an integral domain, M is a free R module of rank n, and n is a submodule of M. So what do we know about M? We know that any n plus 1 elements of M are linearly dependent. And n is a submodule of M, so certainly elements of n are also elements of M. So any n plus 1, where now I'm using the little n, the rank, any n plus 1 elements of this submodule are also linearly dependent. So the rank of this submodule n is at most n. Any n plus 1 elements in the submodule are linearly dependent. The rank is at most n. So this is a statement that we're going to use in our proof of the classification of modules over a PID. So I want to emphasize that the rank of an R module is something that's a little tricky to deal with in general. So remember, we saw this example of R equals z adjoint square root of -5. And we had the ideal inside this ring generated by 2 and 1 plus the square root of -5. This is a non-principal ideal inside this ring. This is an R module. And we saw that any two elements of I are linearly dependent. So what does that mean? That means that the rank of I is 1. But there's no spanning set of size 1. This is a good example of a module that is not free. So this is a submodule of a free module. If you take M equals R as a left R module over itself, I is a submodule. This is an example of a submodule of a free module that is not free. And what we'll see in the next video is that this type of thing cannot happen when R has additional nice properties, like when R is a principal ideal domain.